Hello students, welcome to E-Patasala. I am Dr. Kalayarasi, Assistant Professor in the Department of Textiles and Clothing, Avanashingam Institute for Home Science and Higher Education for Women, Coimbatore, Tamil Nadu. Today, we will have an insight about different effluent treatment methods. You all know that the textile processing industries consumes large volume of water that is required for various processes including desizing, scouring, bleaching, mercerization, dyeing and printing. These industries releases a wide variety of pollutants during the processing of fibers, fabrics and garment construction. About 200 liters of water are used to produce 1 kilogram of textile material. About 30% of water is used for bleaching and 16% for dyeing. Most dyes used in textile industries are stable to light and are not biodegradable. The wastewater released by the textile and dyes of industries is highly polluted. These waste causes damages to ecological system and have to be treated due to their impact on water bodies and growing public concern over the toxicity and carcinogenicity of the pollutants. So, knowing about the different treatment methods is a need of the hour. The objective of effluent treatment method is to enable the students to gain knowledge about different effluent treatment methods, to know about different effluent parameters. The effluents are treated in 3 stages. They are primary treatment, secondary treatment and tertiary treatment. Now, we will have an overview about the different primary treatment methods. The main objective of primary treatment is to remove suspended solids and bring the pH to neutral range. Primary treatment method includes screening, sedimentation, equalization, neutralization and coagulation. Screening. Screening is the first step of primary treatment which removes larger suspended particles such as fibers, yarns, pieces of fabric, lint, etc. Removal of these substances is important as these may clog pipelines, generators, pumps and machineries. Screens of various sizes and shapes are used depending on the nature of solid to be removed. Short fibers and smaller suspended particles are removed by fine screen. Larger suspended particles are removed by coarse screen, which consists of metal bars or heavy wires spaced 25 to 50 mm apart. They are placed at an angle of about 60 degrees to the horizontal axis of the flow or curved to the radius of a circle. Fine screen consists of woven wire or perforated plates and its pore size ranges from 0.18 mm to 0.4 mm. The screens must be cleaned at regular intervals. Nowadays, modern mechanical screens are used. These screens are of 2 types: rotary, self-cleaning, gravity type units and circular, overhead-fed, vibratory units. After screening, the effluent undergoes sedimentation. Sedimentation is a process of settlement of larger particles by gravity. It is an essential prerequisite for secondary treatment. It removes fiber and scum. Most of the solids settle along with heavy metals. The sludge formed at the bottom of the tank is removed as underflow by vacuum suction. Now, let us see the third primary treatment method, that is equalization. Different kinds of waste are produced by various textile processes and discharged at different intervals. Hence, treatment cannot be done as the effluent exhibit different characteristics from time to time. Treatment will be effective only when the parameters such as BOD, pH, etc. are constant. Effluents from various processes are collected in a holding tank to make the characteristics of the effluent uniform. This process of stabilization of pH and BOD is called as equalization. The size and shape of the equalization varies with the amount of waste generated. It should have the capacity to hold the entire effluent generated. Proper mixing of wastewater is brought about by appropriate distribution and baffling, mechanical agitation and aeration. Several inlet pipes were spaced at regular intervals across the width of the tank for thorough mixing. Mechanical agitators are placed along the center of the tank spaced equidistantly. There are several advantages of equalization process. It reduces the cost of treatment by mixing acidic and alkaline effluents, thereby bringing the pH to neutral. It prevents the shock loading on secondary treatment. Equalization will bring down the pH of the effluent which will otherwise hinder the secondary biological treatment systems. Neutralization. The effluents from textile processing industries have extreme pH value. Hence, it has to be treated before letting out into the environment or for secondary treatment. The effluent of acidic nature will corrode the cement, concrete and metals of the pipeline, pumps and other structures. It also de-emulsify the fats, grease and soaps etc. and produce sticky gums which may block the pipelines. Alkaline effluents are also dangerous as it is corrosive in nature. Hence, textile effluents have to be neutralized before discharge into the environment. There are two methods of neutralization. One is neutralization of acid waste and neutralization of alkaline waste. First, we will see how acidic effluents are neutralized. One of the effective and cheapest method of neutralization is mixing the acidic effluent with alkaline effluents in a large holding tanks. Mixing of the effluents may be controlled using valves. Another method is lime slurry method. Lime slurry is the cheapest source for neutralizing large volume of acidic effluent. In this method, the sludge is produced in voluminous and take more time. The third method is caustic soda method. The most effective neutralizing agent is caustic soda. The advantages of caustic soda method over other methods are: hardness of the wastewater is not increased, only smaller amounts of caustic soda are required and very smaller volume of sludge is formed. The disadvantages of this method is that the caustic soda is expensive and hence cannot be used for treating large volume of water. Neutralization of alkaline waste. Alkaline effluents are neutralized by two methods. The first method is treatment with sulfuric acid. This method is the most efficient method of neutralization of alkaline waste. Predetermined amount of sulfuric acid is added to the alkaline waste. Only smaller volume of sulfuric acid is required. The disadvantage of this method is that sulfuric acid is expensive and highly corrosive in nature, hence difficult to handle. So it requires special materials for storage and pumping. The second method is boiler flue gas treatment. Carbon dioxide present in boiler flue gas acts as a neutralizing agent. It reacts with alkaline waste and form carbonates. The equipment consists of a blower, pipeline to carry the gas, filter to remove the sulfur and unburned carbon particles, and a gas diffuser for diffusing carbon dioxide into wastewater. This method is economical, but pH can be reduced only up to 9. The final primary treatment method is coagulation. Coagulation means treatment of water with coagulants to remove colloidal and fine suspended impurities. The particles are destabilized and aggregated to form floc by the addition of some chemicals. The formed flocs absorb and entrap the suspended particles and settles rapidly. Most commonly used coagulants for the treatment of textile effluents are alum, ferric sulfate, ferrous sulfate, chlorinated copperas, ferric chloride and calcium chloride. To enhance the process of coagulation, some chemicals are added in smaller quantities such as activated silica and polyelectrolytes that promote the rapid settling of flocs. These chemicals are called as coagulant aids. They act by reducing the charge on the colloid. There are 3 steps involved in coagulation. They are flash mixing, flocculation and settling. In flash mixing, the coagulants, coagulant aids and chemicals for pH adjustments are rapidly mixed for 4 to 6 minutes in a smaller tank for greater dispersion. The second step is flocculation. The process of floc formation is called flocculation. The flash mixing is followed by gentle stirring of wastewater and coagulants in a larger tank for 15 to 45 minutes for formation of flocs without being broken down by the turbulence. The final step is settling. The flocs form, entangle other suspended particles and settle quickly, leaving a clear supernatant liquid. A period of 1 to 6 hours is required for settling. In this process, BOD is reduced by 63%. For small textile mills that cannot afford for secondary treatment, primary treatment with a final chemical coagulation is effective and attractive. Formation of large quantities of sludge is a major disadvantage in this technique. So far, we have seen the different primary treatment methods. Now, we will pass on to secondary treatment methods. The effluent from the primary treatment contains dissolved organic material and small amount of suspended solids. In secondary treatment, biological action is used to remove the organic materials. Complex organic molecules are broken down into simpler substances by microorganisms during secondary treatment. Hence, secondary treatment is also called as secondary biological treatment. The objectives are to remove dissolved and residual organic matter and reduce COD, BOD and toxicity of the effluent. There are two types of secondary treatments. They are aerobic and anaerobic. Aerobic treatment involves oxygen for the degradation of organic molecules by aerobic microorganisms, and the end product is carbon dioxide and water. Anaerobic treatments are reductive and take place in the absence of oxygen. The end product is methane. Aerobic treatment is most widely used as it is more rapid. There are four types of aerobic process. The first method is activated sludge process. The most versatile biological oxidation method for treating textile waste is activated sludge process. In this method, the textile effluent after primary treatment is fed into an aeration tank where it is subjected to continuous biological degradation by microbial flocks suspended in the reaction tank. Oxygen is supplied by diffusers or by surface aerators. The effluent from the aeration tank is passed to sedimentation tank for settling. A part of the sludge is returned to the aeration tank for effective microbial population. The time required for activated sludge process ranges from 6 to 12 hours depending on the pollution load. The active centers of biological oxidation are microbial mass, which include bacteria, fungi, protozoa and nematodes. Among these, bacteria are the most important as they are the workhorses that degrade the organic substances. Oxygen is an important material for the activated sludge process. A minimum of 0.5 mg per liter of oxygen should be present. Essential nutrients should be supplied for the growth of microorganisms. pH is an important parameter that determines the efficiency of the treatment. Hence, activated sludge system should be maintained at an optimum range of 6.5 to 9. By this method, BOD can be reduced up to 95% and color up to 80%. This method requires lower capital investment and maintenance. The disadvantages of this technique is that they are sensitive to shock loads of toxic and organic substances and they produce larger quantities of sludge. Trickling filtration. Trickling filtration is an effective aerobic biological oxidation process. In this method, the textile effluent after primary treatment is sprinkled over a bed of broken stones. The microbial film formed on the stones oxidizes the organic waste present in the effluent during its passage. The treated effluent is allowed to settle and then discharged. Trickling filters are also termed as biofilters and percolating filters. The most common trickling filters are circular. The wastewater is sprinkled by moving or fixed sprinklers. Trickling filter does not require inoculation but develops its own population, which is a complex mixture of bacteria, fungi, protozoa, algae and larger organisms like insects and worms. The aerobic microorganisms form a gelatinous film on the surface of the stone and oxidize both dissolved and colloidal organic matter into simpler substances. The emergent liquid is free from degradable organic matter. The removal of organic matter depends on the pollution load, temperature, size of stone, microbial surface area, depth of the filter, retention time and oxygen transfer. The growth and metabolic activities of microbes are affected by temperature of the wastewater. Lower temperature decreases the efficiency of degradation, whereas higher temperature kills microbes. Hence, optimum temperature should be maintained. The shape of the stone should be spherical, ranging from 2 to 10 cm in size. Smaller stones are preferred as they have maximum surface area. For maximum efficiency, thin layer of the microbial film should be formed. Usage of plastic and PVC material instead of stones are efficient. The depth of the filter bed ranges from 1 to 3 meter. The base is constructed with vitrified clay blocks as it can withstand the corrosive nature of the waste. The filter is connected with a sedimentation tank where final settlement occurs. The advantages of this technique is they remove BOD by 40 to 85%, suspended solids by 80 to 90% and dissolved solids up to 30%. The treated effluents are of better quality and it recovers quickly from shock loads of toxic substances. Now, let us see the third method of secondary treatment, that is aerated lagoons. Aerated lagoons are activated sludge units operated without sludge return. In this method, large holding tanks or ponds are lined with cement or butyl rubber or polythene. The depth of the tank varies from 3 to 5 meter. The effluent after primary treatment is passed on to these tanks and aerated mechanically. Required oxygen is supplied by floating aerators. The contents of the lagoon are mixed, which enhances the oxidation of dissolved organics present in the effluent. Retention time varies from 2 to 6 days. Advantages: BOD is removed by 90%. Operation and maintenance are simpler. Able to resist shock loads of toxic substances, and it is efficient in treating variable waste. The disadvantages are reduced performance during winter. Treated effluent from lagoons contain bacteria and hence need further purification. Oxidation ponds. The oxidation pond is a simple and economical method for textile effluent treatment. An oxidation pond is a large shallow pond in which effluent is added at one end and treated effluent is removed at other end. Oxidation of organic waste is brought about by bacteria and flagellated protozoa. Oxygen is supplied by the algae present in the pond. More the algae, more will be the amount of oxygen released, which in turn increases the rate of purification. The growth of the algae is enhanced by the nutrients present in the waste. If the waste lacks essential nutrients, it has to be supplied. For light penetration, mixing of the waste by wind and natural aeration, the pond is built shallow. The bottom of the pond is covered with polythene sheeting or linings of bitumen and asphalt to prevent seepage. Concrete slabs are placed at the sides to prevent vegetation and erosion. The retention time varies from 10 to 30 days. By this method, reduction in BOD is achieved up to 80%. We have discussed about aerobic secondary treatment methods. Now, let us have an overview of anaerobic digestion. Anaerobic digestion is carried out mainly for the digestion of sludge. In this method, digestion is carried out in the absence of air in a closed chamber of depth of about 6 meters. The organic wastes are converted into methane, ammonia, hydrogen sulfide and organic acids by microorganisms. The retention period ranges from 10 to 12 days. For effective treatment, the contents are made uniform by stirring. The temperature is maintained at 35 degrees centigrade. BOD reduction is achieved up to 80 to 90%. The advantages of anaerobic digestion is that the process produces much less biomass or sludge. No aeration is required and accompanying smell is less as the process is enclosed. The disadvantages of anaerobic digestion are that the process requires good mixing, a temperature of 37 degrees centigrade, long retention time and a substrate with high BOD. Tertiary treatment. Tertiary treatment is carried out to remove dissolved inorganic solids, colorants, non-biodegradable organics and metals. It is also called as advanced wastewater treatment. It involves physical, chemical or biological processes or their combinations depending on the impurities to be removed. Under tertiary treatment, first we will see reverse osmosis. Reverse osmosis can remove particles ranging in size from 0.001 to 0.01 micrometer and can operate at 90% efficiency. The process of osmosis can be reversed by applying sufficient pressure to the concentrated solution to overcome the osmotic pressure. Reverse osmosis creates microscopic openings so that only water molecules pass through. When textile dye effluent is passed through the semi-permeable membrane, a concentrated dye solution is left over. The most commonly used membranes are cellulose acetate butyrate, and cellulose triacetate. Advantages: this method is excellent for color removal and recovery of dyes, heavy metals and sizing materials. Disadvantages are the membranes are expensive and has to be replaced frequently as the dyes clog the membranes. The next process is electrodialysis. The electrodialysis process uses a series of high capacity, a highly cross-linked ion exchange resin which selectively transfers ions but not water. In contrast to the reverse osmosis, electrodialysis employs the removal of solute from the solution rather than the removal of solvent. This process uses selective permeable membrane and an electrical potential difference to extract ions from solution. Two types of membranes, anionic and cationic, are arranged alternatively to form many compartments between the electrodes placed at the two ends. When voltage is applied across the cell containing wastewater, the anions migrate to the positive electrode and the cations migrate to the negative electrode. This causes solution in alternate compartments to become more concentrated, while that in the remaining becomes more dilute. The process does not require any chemical additives and has low energy requirement. A major disadvantage in this process is that the organic molecules are not removed and they may clog the membranes. This process also leaves concentrated wastewater which requires a high degree of treatment. Activated carbon adsorption. Adsorption on activated carbon is one of the major effluent treatment techniques for the removal of organic and inorganic substances. Adsorption is a surface phenomenon, and larger the surface area, greater is the adsorption. Activated carbon is prepared by subjecting charcoal of carbon material to oxidizing steam at higher temperatures of about 1700 degrees Fahrenheit. The effluent is passed over the bed of activated carbon. The organic and inorganic waste present in the wastewater is adsorbed onto the adsorbent by weak forces such as van der Waals forces. The effluent emerges out free of contaminants. Lint and suspended solids affect the efficiency of adsorption process. Hence, they have to be removed prior to passing through the activated carbon. Advantages: lower cost and simplicity in operation. To conclude, the significance of water is universally known, and the value of life depends on the ability to manage available water in the greater use of people. The production processes of textile materials involve larger utilization of water, which results in the release of polluted water. Hence, it is important to explore various treatment processes for the reduction of pollution load and reuse of the treated water. The time has come to move towards ecosystem specific discharge standards to maintain the health and productivity of natural resources on which majority of people are dependent. Innovative technologies should be developed for minimal utilization of water and its reuse. Go green is the buzzword today. So, the chemical non-biodegradable dyes can be replaced with eco-friendly natural dyes, and conventional chemical processing can be carried out with enzymes. Thank you.